Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss the chain rule for functions of 2 and 3 variables. And really we will see that really the situation or applying the chain rule for functions of 2 and 3 variables is to some extent similar to the chain rule for functions of 1 variable. So it is better just to recall the chain rule for functions of 1 variable. So let's just recall the chain rule. In Math 101, when we have a function y equals of u and u is also a function of g of x, we ask what is the derivative of y with respect to the last variable x. If we draw a diagram, so just indicating the relations of how the variables are related, we have y a function of u, and u a function of x. Our objective is to find the derivative of y with respect to x. Is y a function of x? Of course, yes. If we combine these together, we get the following: y equals of g of x. So really y is a function of x, so it is natural to ask what is the derivative of y with respect to x. In Math 101, to find the derivative of y, the first variable, with respect to the last variable, first we differentiate in a chain. First we differentiate y with respect to u, then differentiate u with respect to x, and then multiply the two quantities. So to find the derivative of y with respect to x, we find derivative of y with respect to u, du, times derivative of u with respect to x, du, dx. And this is the chain rule for functions of 1 variable. For functions of several variables, in fact, there are more than one version for the chain rule. So we give 3 versions, and other versions can be made after these 3 can be made really easily and in a very natural way. Okay. So let's take the first version of the chain rule in Math 101, or for functions of 3 variables, for example. So let's take w equals of x, y, z, a function of 3 variables. X is a function of t, g of t. Y is a function of t, h of t, and z equals k of t. So each of x, y, and z is a function of one variable t. Our objective is to find the derivative of w with respect to the last variable t. This is the objective. Really, to find the formula for the derivative of y with respect to t, here it is better to draw a tree diagram to relate the variables. Okay. So we have first w, a function w. It is a function of 3 variables, x, y, and z. So we have this tree. This is x, and this is y. This is z. This indicates that w is a function of 3 variables. Then we go to each variable x, y, and z and see what kind of functions are they. X is a function of 1 variable t. So I take x to t. Y is h of t, a function of 1 variable t. So I just connect it with the 3rd variable t. And z is also k of t, a function of 1 variable. So I connect z with its variable t. So I have w, the initial, the first variable, t, the last variables, and x, y, z, the intermediate variables. Okay. The main question is, what is the derivative of w with respect to t? What is the derivative of w, the first variable, with respect to the last variable t? Is w a function of t? Yes. In fact, I can again find the composition. This gives us the following. In fact, w equals of f. X is just g of t, and y is h of t, and z is k of t. So w is a function of t, of 1 variable t. So it is natural to ask what is dw, what is dw, dt. Okay. Notice I use the ordinary notation for ordinary derivative, dw dt, because w is a function of one variable, t. How to find dw dt? dw dt. Okay. We ask ourselves, through how many paths can we go from w to t? In fact, we can go from w to t through three paths, through x, through y, through z. Then apply the chain rule of Math 101 through each path, okay, as was given here. Then just add them, So the first path, well, partial w, partial x, times dx dt. Plus, through the second path, apply the chain rule in Math 101, it is partial w, partial y, times dy dt. Plus, through the last path, partial w, partial z, times dz dt. So it is really applying the chain rule of Math 101 through three paths, three times. Okay. So this is the formula for the derivative of w with respect to du. Before we go to the second and third version, notice the notation here. We have d and then the partial. Okay. If for functions of one variable, we use the ordinary notation d. For the functions of several variables, we use the partial notation. So we check w is a function of x, y, and z. W is a function of three variables. So when you talk about derivative with respect to these three, we use partial. So here partial w with respect to s, partial with respect to y, partial w with respect to z. But when you go to x equals g of t, y equals h of t, z equals k of t, each of them is a function of one variable. So here it is the ordinary derivative. So dx dt, dy dt, dz dt. But this is the distinction between the d and the partial. A second version, well, let's take w as a function of f of x, y, z, a function of three variables. But now x is a function of two variables, r and s. Y, h of rs, z, k of rs. X, y, z are functions of two variables. We need to find the derivative of w with respect to the last variables, r and s. How to do that? It is better to draw a tree diagram connecting the variables. Okay. So I have w, a function of three variables, x, y, and z. Then x is a function of two variables, r and s. Y is a function of r and s. Z is a function of r and s. Draw this tree diagram. Now I need to find the derivative of w, the first variable, with respect to the last variables, r and s. So now w is a function of two variables, r and s. Okay. So what is the partial derivative? Partial derivative of w with respect to r. Okay. We ask ourselves, through how many paths can we go from w to r? Okay. I can go from w to r through three paths. Through the intermediate variable, through x first, wxr, and through y, wyr, and through z, wzr. Okay. Through each path, apply the chain rule of Math 101. So through the first path, this is partial w, partial x, then partial x, partial r. Plus the second path, through y, partial w, partial y, times partial y, partial r. Plus, through the last path, through z, partial w, partial z, times partial z, partial r. So this is the formula for the derivative of w with respect to r. In a similar way, we can find partial derivative of w with respect to s. We can go from w to s, through three paths, through the intermediate variables x, y, and z. And through each path, we apply the chain rule of math 101. So this, we go partial W partial X partial S plus partial W partial Y times partial Y partial S plus partial W partial Z times partial derivative of Z with respect to S. So this is the formula for partial W partial S. This is a second version. A third version is given as follows. We have W is a function of X, one variable, and X is a function of two variables, R and S. We draw a tree diagram connecting the variables. So W is a function of only one variable X. X is a function of two variables, R and S. We need to find the derivative of W with respect to R and with respect to S. With respect to R and with respect to S, W is a function of two variables. So what is the partial derivative of W with respect to R? Again, through how many paths can we go from W to R? We can go from W to R through only one path, which is X. So through this path, apply the chain rule of math 101, which is partial dW dx times partial X partial R. It's a function of one variable. Use dW dx. From X to R and S, it is a function of two variables, so it is partial derivative. In the same way, partial W partial S equals dW dx times partial X partial S. So this is a third version of the chain rule. Understanding these three versions, in fact, we can derive and we can set up many other versions. Okay. One last note before we close this one. Here I gave the versions here for functions of three variables. What about if W is a function of two variables? If Z is missing? Well, if Z is missing, then just delete this tree, this branch of the tree diagram, and then delete the last term. The same thing here. If Z is missing, then delete this branch and delete the last two terms. This is actually the only difference. Let's now consider the following problem. Let W equals xy plus yz plus zx, and x equals u plus v, y equals u minus v, and z equals uv. Find the partial derivative of W with respect to u in terms of u and v. The problem here is about the chain rule. So you have a function of three variables, and each of these variables is a function of two variables. So the first step is just to find a relation or to connect the variables of the problem. And to make the connection, we draw a tree diagram. So we start with W. W is a function of three variables. So I write W here, W, and I have tree diagram, a function of three variables X, Y, and Z. Then X is a function of two variables, U and V. So I put two more branches under X. This is U and V. And the same thing for Y. This is U and V. And the same thing for Z. This is U and V. So this is the connection between the variables of the problem. We need to find the partial derivative of W with respect to U. So in that case, to apply the chain rule, just we ask through how many paths or through which path can we go from W to U? We can go from W to U through X and through Y and through Z. So three paths. This is the first path, the second path here, and this is the third path. Through each path, we apply the chain rule of math 101. So partial W, partial U equals, through the first path, it is partial W, partial X times partial X, partial U, plus through the second path, partial W, partial Y times partial Y, partial U, partial Y, partial U, plus through the last path partial W partial Z times partial Z partial U. So this is the formula of the chain rule for finding partial W partial U. Now you just substitute each quantity, the value of each quantity. So the derivative of W with respect to X, the first term is Y, the second term is 0, the third term is Z plus Z times partial X partial U. The derivative of X with respect to U is just 1. Partial W partial Y with respect to Y, here I get X. With respect to Y I get here Z. With respect to Y I get 0. Partial Y partial U, partial Y partial U, it is just 1. Plus partial W partial Z with respect to Z, this is 0, this is Y. Plus with respect to Z, this is X. Partial Z partial U, this is just V. This is V. So this is the first step. Of course, the answer is given here in terms of X, Y, Z, and V, but we need the answer to be in terms of U and V. So in that case, we have to just substitute X, Y, and Z in the given expression. So here, just this we can just simplify a little bit. This is Y, Z, X plus Z. So this is X plus Y, X plus Y plus 2Z plus X plus Y times V. Okay. So what is X plus Y? If we add X plus Y, you get 2U. You get 2U. So this is 2U. This is for X plus Y. Plus 2Z, 2UV, 2UV, plus X plus Y, again it is 2U, this is 2U, times V, When you add, you get the following, 2U plus 4UV, or if you want, this is just 2U times 1 plus 2V. So this is the answer in terms of U and V. Now we consider the following problem. Let Z equals tan inverse X over Y, X equals U cosine V, Y equals U sine V. Find the value of partial derivative of Z with respect to V when UV equals root 2 pi over 4. Here it is a problem about the chain rule. We can find the derivative of Z with respect to V by using the chain rule. And for that, we need to draw a tree diagram first to connect the variables of the problem. So here we have Z, this is Z. It is a function of two variables, X and Y, and X and Y, U cosine V, U sine V. Each is a function of two variables, U and V, and Y is also a function of two variables, U and V. We need to find the partial derivative of Z with respect to V. So we look through the paths going from Z to V. From Z to V, I can go through two paths. The first one is through X, and the second one is through Y, through this path. Through each path, I use the chain rule of Math 101. So here, partial Z, partial V equals, along the first path is partial derivative of Z with respect to X times partial X with respect to V. Plus, through the second path, it is partial Z, partial Y times partial Y, partial V. So this is the formula of the chain rule for finding the partial derivative of Z with respect to V. Now we compute each quantity. Now, partial derivative of Z with respect to X. Now here we have to recall what is the derivative of tan inverse. So just recall that really derivative, ddx from Math 101, or ddt, let's say, ddt of tan inverse t equals 1 plus squared. So this is the derivative of tan inverse t from math 101. Now for here I have partial derivative of z of tan inverse with respect to x. So here the derivative of tan inverse is 1 over 1 plus the argument, which is x over y squared, times, well, I have to use the chain rule to differentiate with respect to x. Derivative of x over y with respect to x is just 1 over y. So this is 1 over y. This is for partial z, partial x. Now times partial derivative of x with respect to v. Partial derivative of x with respect to v, this is minus u cosine sine v. U will be fixed, will remain constant. The derivative of cosine v is minus sine v. This is for the first term, plus the second term, derivative of z with respect to y. Derivative of tan inverse, it is 1 over 1 plus x over y squared by the chain rule. Derivative of x over y with respect to y, this is minus x over y squared. So this is partial derivative of z with respect to y, times partial derivative of y with respect to v. This is u. Derivative of sine v is just cosine v. So this is the formula. Here there is no need to simplify, okay, because I need the value of this expression when u equals root 2 and v is pi over 4. So I can leave it like this. I need to substitute u and v as given, and find x and y, and then substitute. Now from the formula for x, this is x here, it is u cosine v. So it is u root 2 cosine pi over 4. And this is root 2 times 1 over root 2, and this is just 1. The same thing for y equals u, which is root 2 sine v, which is pi over 4. And this is root 2 times 1 over root 2, and this is again. So x, when u equals root 2, v equals pi over 4, x is 1 and y equals 1. So I substitute here for x, y and uv. So this becomes 1 over 1 plus 1 over 1 squared, this is 1. 1 over y is 1, so this is 1. Minus u sine v, when you substitute you get minus. Notice this is minus y, so this is just minus 1 plus 1 over 1 over 1 squared is just 1, minus again 1 over 1 u cosine v, which is just x is just 1, again this is just 1. So this is minus half, plus, again this is minus half. So the answer is just minus 1. This is the value of the given partial derivative. We consider now the following problem. Let z equals ln x squared plus y squared, x equals e power t minus t, and y equals 2 plus t. Find the derivative of z with respect to t. Again, we can use the chain rule. Okay, here just so that for that we just connect the variables of the problem. So we have z is a function of two variables, x and y, and x is a function of one variable t, and y is a function of one variable t. So this is x, a function of one variable t, and y is a function of one variable. We need to find the derivative of z with respect to the last variable. Notice here we write dz dt. So this is the ordinary derivative, because at the end z is a function of only one variable. So now this is why we write dz dt. To find dz dt, again we can go from z to t through the two paths, through x and through y. So we find the derivative through the first path, through the second path, and then we add them. Through the first path, this is partial z, partial x, because z is a function of two variables, so we use the partial, times dx dt. Ordinary derivative, because x is a function of one variable, plus the second path, partial z, partial y, times dy dt. So this is the formula for the derivative of z with respect to t. Now we compute each term. Partial derivative of z with respect to x. When you differentiate this with respect to x, this is 1 over x squared plus y squared times, using the chain rule, this is just 2x plus 0. This is for partial z, partial x, times partial derivative of x with respect to t. Derivative here, this will be e power t minus 1, plus partial derivative of z with respect to y. Again, this is just 1 over x squared plus y squared times, when you differentiate with respect to y, this is just 0 plus 2y times dy dt. dy dt is just 1. So this is the formula. Now we simplify our work, so this becomes x squared plus y squared, and this is 2x e power t minus 1 plus, this is x squared plus y squared. The denominator is just 2y. The numerator is just 2y. You have the common denominator here. So this is just x squared plus y squared. When you add these together, notice that 2 is a common factor, so I will take just the 2 outside. What remains is just x e power t minus 1 plus y. So we leave the result in terms of x, y, and t. This is the answer. Okay. We consider the following problem. Let w equals of f of u squared minus v squared, comma v squared minus u squared. Show that v times partial derivative of w with respect to u plus u times partial w with respect to v equal to 0. So how to show that really this expression equal to 0? Here, what is f? F is really not known, but it is given that it is really a function of two variables. The first variable u squared minus v squared, the second variable v squared minus u squared. So it is better now, really, it is better just to write it really as a function of two variables. So here, just give this a name. Instead of being a function, just give it a name. And this is also, give it another name, to indicate that really it is a function of two variables. So solution here, first, let x equals u squared minus v squared, and y be the other quantity, which is v squared minus u squared. Then we have the following then. W equals of x, comma y, where x is just u squared minus v squared, and y equals v squared minus u squared. When we write it in this manner here, well, this will give us an indication really to find derivatives. We have to use the chain rule. Here you have w, a function of x and y. X and y is a function of u and v. So to find partial derivative of w with respect to u and with respect to v, we have to use the chain rule. Even so here we didn't know what is exactly the function f, but still we leave it as it is. Now to find partial w with respect to u and with respect to v, apply the chain rule. And to apply the chain rule, we have to just connect the variables. So we have w here. W is a function of x and y, and x is a function of u and v, y is a function of u and v. So we have to find partial w, partial u. So here partial w, partial u. As usual, by the chain rule, through x and through y, we can go from w to u through x and through y. Through x, it is partial w, partial x, times partial x, partial u. Plus, through y, it is partial w, partial y, times partial y, partial u. So this is the first one. Compute, so this equals, what is partial w, partial x? What is the derivative of w with respect to x? Well, we don't have a formula or an expression for f, so we cannot really calculate it. So we just leave it as it is. So it will remain partial w, partial x, times partial derivative of x with respect to u. This will be 2u, plus partial w, partial u, y. Again, there is no expression for f, so we leave this as it is. Partial w, partial y, times partial derivative of y with respect to u. This becomes minus 2u. So this is the partial derivative of w with respect to u. We do the same thing for partial w, partial v. This is partial w, partial v equals, again, through x and through y. This is partial w, partial x, times partial x, partial v, plus, just like computing the first one, partial w, partial y, times partial y, partial v. Compute each, again, partial w, partial x. We leave it as it is because there is no expression for f. So this is partial w, partial x, times partial x, partial v, partial x, partial v, minus 2v, plus partial w, partial y, again as it is, times partial y, partial v. This is 2v. So these are the partial derivatives of w with respect to u and v. Now we need to just substitute this. So multiply v by this plus u times this and see what we get here. Okay, so here I will just multiply this by v and multiply the second by u. Okay, and notice what will happen. So let me write the answer here. So this is v partial w, partial u, plus u partial w, partial v. When I multiply this by v, I get 2uv, partial w, partial x, minus 2uv, partial w, partial y, plus, now multiply u by partial w, partial v. Multiply it here. This becomes minus 2uv, partial w, partial x, partial x, plus 2uv, partial w, partial y, partial y. Now you add, and as you can see, it is easily that these two terms will be cancelled out. Okay, positive and negative, they will cancel. With respect to y, this is y, coming off from this one. Again, they will cancel out. Negative and positive, they will cancel. So this is really 0 plus 0, and hence the answer is 0. Let's consider the following problem. Let f of u v w be a differentiable function and u equals x minus y v equals y minus z, w equals z minus x. Find f sub x plus f sub y plus f sub z. Simplify your answer. So here we need to find the partial derivative of f with respect to x, with respect to y, with respect to z, and then add them and see what we get. It is a chain rule, a problem about the chain rule. We have just to relate the variables. Here we have f, just let's give it a name. So let me write solution here, solution. So just let me write m equals of a few v and w. So we have m, a function of three variables. u, v, w here, u, v, w, they are given there. We need to find f sub x and f sub y and f sub z. And when I write m here, this means really f sub x is partial derivative of m with respect to x. And f sub y is just partial derivative of m with respect to y, and partial z, f sub z is just partial derivative of m with respect to z. This is the meaning of the given expression. So we need to find partial m, partial x, partial y, partial z through the chain rule. So we have to draw a tree diagram connecting the various variables of the problem. So I have m, a function of three variables, u, v, and w. u, v, and w. u is a function of two variables, x and y, sorry. v is a function of two variables, y and z. And w is a function of two variables, x and z. So each is a function of two variables, and the two variables are different in each case. So now I need to find partial derivative of m with respect to x, f sub x. Partial derivative of m with respect to x. So now let me write it here. So this is f sub x. It is partial derivative of m with respect to x. Now I can go from m to x through how many paths? Through two paths. The first path, this is the first path, m and x. There is no x after v, so I cannot find partial m, partial x through v. I have x through w, so this is the second path. So I have the derivative with respect to x through these two paths. So it is partial m, partial u. This is partial m, partial u times partial u, partial x, plus partial m, partial w, times partial w, partial x, partial x. And let me just compute this. Partial m, partial u, again, we don't know, and we don't have any expression for f, so the partial m with respect to u will remain as it is, just as a notation, as an expression. So this is partial m, partial u, times partial u, partial x. Well, partial u, partial x, it is just 1. This is 1. Plus partial m, partial w. Same thing here. M is a function of three variables, u, v, w. But there is no expression for f, so we leave the partial derivative as it is. Partial m, partial w, times partial w, partial x. When you differentiate w with respect to x, you get minus 1. So this is partial m, partial x. We do the same thing for f sub y and f sub z. So this is f sub y, quickly here, f sub y. This is partial m, partial y. And through y, we have just these two paths. through x and y. So this is partial m, partial u times partial u, partial y, plus partial m, partial v, partial y. Just like the previous case. Again, as above, so this is partial m, partial u, partial y, this is just -1, plus partial m, partial v, times partial v, partial y, this is just 1. The last one, f sub z, this is partial m, partial z. For the z, I can go just through v and w only. So this is partial m, partial v, partial m, partial v times partial v, partial z, plus partial m, partial w times partial w, partial z. Computing as done, similar to what we did above. So this is partial m, partial v times partial v, partial z. This is just -1, plus partial m, partial w times partial w, partial z. It is just 1. So this is the computation of the partial derivatives. Now we need to add. And so when we add, we get the following here: f sub x plus f sub y plus f sub z equals. We add these quantities here, and let's notice the following here: partial m, partial u, partial m, partial u, 1 and -1. So they are negatives of each other. So when we add them, we get 0. This is 0. Partial m, partial v times 1 minus partial m, partial v. So these will again will be cancelled. Okay. So this is 0. And the last two terms, minus partial m, partial w plus partial m, partial w. So when we add them, we get also 0. So the sum will be just 0. So this is the answer. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss implicit differentiation for functions of two variables. The situation in general is really similar to implicit differentiation in Math 101 with functions of one variable. We can do exactly the same thing for functions of two variables, but also we can do better. We can give a formula really for the derivative with respect to x and with respect to y for a function defined implicitly. And this is what we will concentrate on in this video. And for that, we have the following theorem here. So let f of x, y, z be a differentiable function. If the equation of x, y, z equal to 0 defines z implicitly as a differentiable function of x and y. Okay. So we may have an equation just like, for example, the example here, we may have x, y, z plus sine z minus cosine x equal to 0. We may think of this equation as an equation defining z implicitly as a function of x and y. So z is a function of two variables, x and y. Then how can we find the derivative of z with respect to x and with respect to y? This theorem will tell us how by a formula here. So if the equation, just like this equation, defines z implicitly as a differentiable function of x and y. So z is a function of x and y, but we don't know exactly what is the expression of z in terms of x and y. Okay. Like this. Okay. Then we have a formula for the partial derivative of z with respect to x and partial derivative of z with respect to y. And it is equals minus f sub x over f sub z. This is the function, capital F. So it is just minus the derivative of this with respect to x over its derivative with respect to z. And partial z, partial y equals again minus partial f partial y over partial f partial z. Provided, of course, the denominators are not equal to 0. How to show this? How to prove this? In fact, the situation is here is an application of the chain rule. So let's see how to find at least partial z, partial x, and the other derivative is similar to it. Okay. So to prove the first part, to prove this one, we proceed as follows. Okay. So proof of the first one only, proof. Okay. So I will let W equals of x, y, and z. So now to find partial z, partial x, I will differentiate this expression. I will the equation. Okay. Differentiate now. Differentiate. The equation, both sides of the equations of x, y, z equal to 0 with respect to x, with respect to x. This equation is just w equal to 0. W equal to 0. Because f, capital F, is just w. If I differentiate this with respect to x, what do I get? I get the following. Partial w, partial x equal partial 0 with respect to x. It is just 0. Now what is partial w with respect to x? Well, I have the chain rule here. I have w. I have just w is a function of x, y, and z. It is given that z is a function of x and y. Okay, so it is defined implicitly as a function of x and y. Y is not a function of x. It is just a variable, main variable. X is a function of itself. We can say x is a function of x, of itself. For now, I need the partial w with respect to x. By the chain rule, I can go from w to x through x and through z. Okay. So find partial w, partial x. This becomes partial w, partial x times dx, derivative of x with itself, plus partial w, partial z, partial z times partial z, partial x equal to 0. Well, this gives us the following. Partial w, partial x. What is derivative of x with respect to x? This is just 1. Plus partial w, partial z times partial z, partial x equal to 0. Now I can solve for partial w, partial z, partial z, partial x. This is what we need. I can solve for this one. This implies partial z, or partial w, partial z times partial z, partial x equals, we take this to the other side, this is minus partial w, partial x. Divide by partial w, partial z, provided it is not equal to 0. So this gives us the following. Partial z, partial x equals minus partial w, partial x over partial w, partial z. Okay. But for the notation here, w is a function of w equals capital F of x, y, and z. So partial w, partial x, it is the same thing as f sub x. So this is just minus f sub x at x, y, and z, and partial w, partial z, it is just f sub z. f sub z of x, y, and z. Again, as we said, provided the denominator is not equal to 0. Okay, f sub z at x, y, z not equal to 0. So this is the formula for partial w, partial z, partial x. In a similar way, we can get the second formula. So here we can find partial if an equation defines z implicitly as a function of x and y. In fact, we can find the partial derivative of z with respect to x and with respect to y by a formula. A quick way to find the partial derivative. Let's consider the following problem. If the equation x times e power yz minus y times e power xz equals y squared plus 1 defines z implicitly as a differentiable function of x and y, then find partial z, partial x. So here we have just to apply the formula for partial z, partial x. Just we collect all the terms in one side. So here we have x e power yz minus y e power x z minus y squared minus 1 equal to 0. And we take this to be capital F. Okay, so here let capital F of x, y, z equals x e power yz minus y e power x z minus y squared minus 1. Now to find partial z, partial x, we apply the formula. So here partial z, partial x equals minus f sub x, x, y, z over f sub z, x, y, and z. So this is the formula. Now just compute f sub x and f sub z and then substitute. So here we have the following. Just compute, this is minus. For the numerator, we differentiate capital F with respect to x. When you differentiate this with respect to x, you get e power yz minus, differentiate this with respect to x. So I have y constant times, you differentiate e power xz. And notice that z is differentiate this with respect to x. Sorry, so this becomes e power x z times derivative with respect to x by the chain rule becomes z. Minus this is just derivative with respect to 0, with respect to x it is 0. For the denominator, you differentiate with respect to z. So the first one with respect to z, so x is a constant here. Derivative of this one, this is e power yz times y when you differentiate with respect to z. Minus derivative with respect to z, this is y again. E power x z times, by the chain rule, this is just z. When you differentiate xz with respect to z, you get x. Minus 0. Now simplify if possible. So this is just minus here. This is e power yz minus yz e power xz. That denominator here, I have xy, and xy is a common factor. So this is xy e power yz minus e power xz. So this is the answer. So we can find it really by just applying the formula, which makes it a quicker way to find the partial derivative for functions defined implicitly by some equations. Let's consider the following problem. If the equation x squared z plus y plus x z squared equal to 0 defines z implicitly as a differentiable function of x and y, then find the second partial derivative of z with respect to x, with respect to x and with respect to y. So we need to find second derivative with respect to x and with respect to y. And of course, here the order, we have first to differentiate with respect to y, then with respect to x. But z is a function defined implicitly by this equation. First, we find solution here. Well, the second derivative, the second partial derivative of z with respect to x, with respect to y. This is by definition. We start with y first. So this is partial x of partial z, partial y. This is for the notations. We have to start first differentiating with respect to y, then with respect to x. So how to find partial derivative of z with respect to y? Z is given implicitly by this equation. First we find this one. And again we use the formula. So here I will put this as my capital F. So here let me write F capital of x, y, z equals the whole equation x squared z plus y plus x z squared. This is my capital. So now to find partial z, partial w, partial z, partial y, according to the formula it is minus f sub y over f sub z. This is my capital F. Find f sub y and f sub z. So here this is minus f sub y. When you differentiate this with respect to y, this is 0, this is 1 plus 0, so this is just 1. Over f sub z, differentiate this with respect to z, I get from the first term I get x squared. From the second term it is 0. From the last term it is 2xz. So this is partial z, partial y. So here I write this now here. This is just equals partial x, partial z, partial y. This is the answer. This is minus 1 over x squared plus 2xz. I can take the minus outside. This becomes minus partial x of 1 over x squared plus 2xz. So this is the first test. First we find partial z, partial y. Next I have to differentiate this with respect to x, keeping in mind that z is a differentiable function defined implicitly by this. It is a differentiable function of x and y defined by this equation. Now how to differentiate this with respect to x? Again, the usual, use the quotient rule. So you continue here, this equals the following. Minus, when you differentiate using the quotient rule, so it is the denominator squared, so this is x squared plus 2xz all squared. It is the denominator x squared plus 2xz times derivative of the numerator, which is 1, with respect to x. So it is 0. Minus the numerator, which is 1, times derivative of the denominator with respect to x. So differentiate the denominator with respect to x. So derivative of x squared, it is 2x plus derivative of 2xz. 2 is a constant, so I will leave it 2 as a constant, times derivative of x and z, xz. Remember that z is a function of x and y. So here when to differentiate xz with respect to x, I use the product rule. So it is the first term derivative of the second plus the second term derivative of the first, all with respect to x. So differentiate xz with respect to x. This is the first x term derivative of z with respect to x. So this is partial z, partial x. Plus the second, which is z, term derivative of x with respect to x, it is just 1. This is the derivative. Simplify, so this is just, notice the first term is 0 here, so this is 0, and I have minus with minus, so the minuses will become positive. So I have the following here, the denominator, the numerator is 2x, in this manner. This is 2x plus 2x partial z partial x plus 2z over x squared plus 2xz power 2. So this is when you differentiate with respect to x. But we notice here we need to find partial z partial x. What is the derivative of partial z partial x? Here we use implicit differentiation using the formula. Just like when we find partial z partial y, we find also partial z partial x by using the formula. And our capital F is this one. So here I can find partial z partial x. It is by the formula, it is minus f sub x over f sub z. Compute. Now I have capital F, this is minus here. Okay. F sub x is just 2xz, 2xz plus 0 plus z squared. So this is f sub x over f sub z, this is x squared plus 0 plus 2xz, 2xz. Now I take this and substitute it here, and then simplify. So if we do this, notice first that 2 and 2 is a common factor, so I will take the 2 outside, and then I have the following: x plus z plus x times partial z partial x, which is this quantity. So this is just minus 2xz plus z squared over x squared plus 2xz. The 2 is out. I remain with x plus z plus x times partial z partial x over x squared plus 2xz all squared. What remains is just to simplify. Here, take the common denominator, and when you simplify, the rest is just, so this is 2 times the common denominator x squared plus 2xz, just or another way, multiply numerator and denominator by this quantity, which is the same as this quantity. So this is x squared plus 2xz power 3. This is x plus z times x squared plus 2xz plus and minus, here minus x 2xz plus z squared. Multiply these together, and then add and simplify. We'll leave this for you. It's very simple simplification. So this is how to find the second derivative in this case.